So thanks very much. And thanks to those of you who made it out for the early session on the final day. Um, so yeah, what I will talk about today, and I wish I was there to talk about it in person instead of on Zoom, is localization and instability in kicked quantum matter. And I want to give an outline for the talk and talk about how it fits into sort of a recent sequence of experiments that we've been doing in my group at UC Santa Barbara. So major topic of our research in the last few years has been the dynamics of localized matter. And we also have some work going in a new direction, including a new experiment going towards quantum interactive dynamics. And here are some of the recent results from those various enterprises. Actually, when I talked at ICTS in June, I talked about a few of these experiments highlighted in red here, having to do with dynamics in quasicrystals and multifractal states and so on. And that's not what I'm going to talk about today. Today, instead, I'm going to talk about things that are a little more suited to the topic of this program, having to do with the stability of quantum matter away from equilibrium. And it's really two major experiments in my lab, one of which was the observation of something called the quantum boomerang effect, and the other one of which was the study of the effect of interactions on localization in the quantum kicked rotor. By the way, what should I aim for timing-wise? The whole 40 or 35 plus 5, or what's the general
goal? I think we can go 35 plus 5 for questions.
Okay, great. Let me know if I'm getting along, but I have a clock here too.
Yeah, good.
All right, so these are the two major topics I want to discuss. I want to first go into a little background on localization in the quantum kicked rotor for those of you who are not familiar with this system, and then talk about the two experiments in that order, having to do with the quantum boomerang effect, which is a fundamental dynamical phenomenon in Anderson insulators, and then interaction-driven anomalous delocalization in an ensemble of interacting kicked rotors. So first, a little background. So localization, I think, probably doesn't need too much of an introduction, so I'll whiz through this. It's been understood since at least the work of Phil Anderson in the 50s that disorder can drive a metal into an insulator. And it doesn't have to be real disorder. It can be quasi-periodic disorder as well, or quasi-periodic of various flavors. And this is something that is really a central pillar of modern condensed matter physics. It's been studied a lot, and these papers have a lot of citations. And this is the sort of arena into which the experiments that I'll tell you about today fall. And I hope I can say a few new things about this not very new topic of localized matter. And our main experimental tool is trapped gases of neutral atoms that are kicked pretty hard and driven very far away from equilibrium. So that's a lightning introduction to localization. Now I want to just introduce the central actor in the two experiments that I'll tell you about today, which is the quantum kicked rotor. So the classical kicked rotor is described by the Hamiltonian shown here, and this just represents a kicked particle on a ring. It has some kinetic energy, and it has some pulsed cosine-shaped potential energy, which you can think of as, vibrating the pivot of a rigid pendulum, for example, or turning on and off gravity somewhat more challengingly. And at the classical level, this is a prototypical example of chaos. So as you increase the strength of this parameter k, which multiplies the second term in the Hamiltonian, which is increasing the strength of the kicking, you go from regular orbits in phase space to increasing areas of the phase space that are characterized by chaotic dynamics, and that happens above some particular value of this kicking strength, which is pretty close to 1. The interesting thing about this, from the point of view of this this program, is that the quantum version of the kicked rotor behaves totally differently than the classical version. It's a failure of the correspondence principle in some sense. So what in fact you see for a quantum system is shown in this graph here. So let me just go back and say about the classical kicked rotor that in this chaotic regime, you expect the system to absorb more and more energy from the thing that's doing the kicking. So it heats up and goes to very large kinetic energies. And that's expectation is shown here. This is actually the absolute value of the momentum, which is related to the kinetic energy, of course, as a function of kick number. And for a classical rotor in the regime shown here, you would expect that to grow very rapidly with kick number because it's a chaotic system. The quantum rotor defies this expectation and instead localizes at some finite value of the mean absolute value of the momentum or the mean kinetic energy. And this is a form of ergodicity breaking and localization at some finite energy density. And this is a very well-known phenomenon now since at least the experimental work done in Mark Raisin's group, which is the citation down here at the lower left, and which I think represents one of the very first examples of optical lattice quantum simulation. But I like to really highlight the non-intuitive nature of this because one can lose track of it given that this is a fairly well understood phenomenon. So really what's happening here is you have some quantum rotor and you're giving these very hard kicks over and over and over, and the thing just absorbs a little bit of energy from the kicks and then it stops absorbing energy and just stays that way essentially forever. It's very, very non-intuitive behavior, but straightforward to reproduce in an experiment. Many people have seen this, in particular using cold atoms. So the way this can be understood in the context of the Anderson localized matter that I referred to earlier is as an effect of Anderson localization in momentum space. And that's a little bit striking because there's no disorder in the system at all. But it turns out that the interplay between the momentum space lattice that the kicks drive the quantum system along and the quadratic kinetic energy, which offsets the chemical potential of those lattice sites, gives rise to an effective quasi-disorder, which drives localization. So it was Shmuel Fishman and collaborators who really first understood this, I think, as an example of Anderson localization, and as that being the reason why the system stops absorbing energy and momentum from the drive. So I introduced this system at some length because it is the experimental context in which I want to tell you about some recent experiments exploring a few open questions in the stability or instability of quantum matter far away from equilibrium. So the first such open question concerns the dynamics of localized matter, and I'll tell you about a dynamical phenomenon which is generic to the Anderson insulator, but surprisingly has only recently been thought about, even theoretically. That's the quantum boomerang effect. And then second, I want to tell you about our recent experiment on a topic that many people have thought about, which is the effect of interactions on the stability of this particular flavor of localized matter. So before I do that, the last little bit of introduction here is talking about the experimental realization of these phenomena. So this is done with an optical lattice, and the analogy here is between the rigid pendulum with a kicked pivot that I introduced as the classical physical substrate of the kicked rotor Hamiltonian, and a Bose condensate loaded into a pulsed optical lattice. So we created a BEC using techniques which I won't talk about at all today, but which are pretty fun. And then we turn off the trap, the dipole trap, which holds that BEC. In this case, it's made of lithium-7. And then we apply an optical lattice, as shown by these little orange pancakes here. And the lattice is turned on and off with some period big T and some pulse length tau. Excuse me. And this, for reasonably short pulses, makes an approximation of this very same kicked rotor Hamiltonian. The only slight difference here is that the x variable, the position variable, is now non-compact. It's real position instead of a phase. That doesn't turn out to be important for any of the stuff I'll tell you today, but it does give rise to some interesting subtleties. And so this is the general idea of how we experimentally realize it. This is a picture of the machine with which we do the experiments. So what you see here over on the left, the bundle of tinfoil is a bunch of metallic lithium. We heat it up very hot. It makes an atomic beam, propagates down this rather long tube, and then around the region where all the green and red lasers are shining, the atoms are trapped and cooled in a sequence of stages unto Bose condensation. And once they're both condensed, we can tune their interactions apply the kicked lattice and study their dynamics. Okay, so that completes my the background that I wanted to give today. So what I want to do now is move into a discussion of the first experiment, which is the observation of the quantum boomerang effect. By the way, I'm very happy to take questions as I go along if anyone has them. I don't know what the technology would be or if people can just sing out, but feel free to send a chat message or say anything. Excuse me. Okay, so the quantum boomerang effect. As I mentioned earlier, the quantum boomerang is a sort of surprisingly recently predicted, but pretty fundamental dynamical phenomenon that occurs in localized matter. And these papers that I've put up here are actually the first theoretical papers that kind of realized and thought about this phenomenon. And the basic idea is super simple. But really, it should be understood as a dynamical idea, something that describes the evolution of a system in time. So the idea is if you imagine yourself as a tiny person standing inside a disordered potential, which characterizes an Anderson insulator, and you take an electron wave packet in your hand and throw it away from you, the classical expectation in a disordered landscape like that would be that it would kind of bump along for a while and then come to rest at some distance from you. Maybe that distance would be characterized by the mean free path or some other related length. Instead, in a quantum mechanical Anderson insulator, what happens is that the wave packet goes away from you, turns around, comes back towards you, and then comes to rest back at the position that you threw it from. So not exactly like a boomerang, more like a loyal pet, as I like to say, but I didn't name the effect. I'll go into a little bit more quantitative detail on that later, but basically this is the idea that if you throw something away from you, it's going to come back to you and come to rest right at your feet. And the reason for this is actually super simple. It's a consequence of just two things, which is Anderson localization and time reversal symmetry, and it does depend on both of those. So the argument in sketch form here says that if you consider creating some wave packet with some finite momentum going away from you, then the long time fate of that wave packet must be not time dependent. That's a consequence of localization. That's point one. And point two is that it must not depend on the sign of the initial momentum. That's a consequence of time reversal symmetry, because if you reverse time, the momentum would have the opposite direction. And actually, just those two facts force you to conclude that at long times, the average position of the wave packet must come back to zero, to the original position. And this, as I sort of argued a minute ago, is really an intrinsically quantum mechanical effect. It violates your sort of classical Ehrenfest theorem expectation of what the expectation value of this of the momentum should do. And the reason we can talk about it experimentally is that this can be explored in the quantum kicked rotor because, as Shmuel Fishman told us many years ago, the kicked rotor is itself a momentum space Anderson insulator. So that's the slight twist that's between this theory and our experiments, is we're gonna interchange the roles of position and momentum space. So instead of giving a particle some initial momentum and throwing it away from us in position space, we're going to give it some initial position and then look at the dynamics in momentum space. The people pictured here are our theoretical collaborators who are co-authors on this paper, and in particular, Tomaz Macri actually was my very first visitor after the pandemic ended, and he came and we had a nice chat, sitting outdoors in the way one did in those days, and conceived the idea for this experiment during that visit. And Patrizio Vignolo also was a key part of realizing that we could do this with a kicked rotor. Okay, so this is the experimental protocol here. As I said, we've swapped the roles of position and momentum space. So the procedure is time moves from top to bottom on this cartoon. We load the atoms into one lattice, and then we snap off that lattice and kick with a different lattice that's shifted in position. And so this shift in phase, spatial phase between the two lattices, plays the role of the initial kick that you give the particle, which is now in position space. And then we observe in momentum space the dynamics. So what you would expect to see if the quantum boomerang effect indeed occurs is that if you observe the dynamics of the center of mass of the wave packet in momentum space as a function of time, then it should depart from the origin, come back, and settle at the origin at late times. So without further ado, this is indeed what happens if you do this experiment and you tune things up right. So what you see here in this in these purple dots is the expectation value of the momentum as a function of the kick number out to 50 kicks, and you see that for the first few kicks, the wave packet travels away, then it turns around and comes back, and then for as long as we care to run the experiment, it comes to rest quite close to the origin, not oscillating with the original amplitude, for example. And the reference here at lower right is the paper where we describe this observation. So you can do a little bit more than just look at this. And one of the interesting things you can do is probe the dependence of the quantum boomerang effect, which is really a fundamental diagnostic of Anderson localization, on these two key ingredients, which are localization itself and time reversal symmetry. So the one way to probe the impact of time reversal symmetry on the quantum boomerang effect is to controllably remove that symmetry. And that can be done in this context by adjusting something we call the Floquet gauge. And this is actually, in practice, a very simple thing. It just corresponds to how long you wait before the first kick. So if you wait exactly half a period before the first kick, that's what this cartoon on the left with the green highlighted period is showing. And if you wait a little bit more than half a period, that's what the cartoon on the right is showing. So other than that small difference, these two experiments have exactly the same protocol. And yet you see that if you adjust the value of this parameter alpha, which is how much of a period you wait, too far from 0.5, the quantum boomerang effect no longer occurs. So the red points in the right-hand graph show that the particle, propagates away from the origin, comes back a little bit, but comes to rest some distance from the origin, more or less as one would expect classically, but not exhibiting the quantum boomerang effect. The reason for this is simply that one of the axioms that supports the occurrence of the quantum boomerang effect is time reversal symmetry. And if you think about the role of the Floquet gauge and what happens if you run time backwards in this experiment, then if you get too far from making your first kick exactly half a period after you drop the atoms out of the lattice, the system no longer actually looks time reversal symmetric. So in this super simple way, we could vary the time reversal symmetry of the Hamiltonian itself. Yeah, is there a question?
Yeah, a quick question here. How do you know that what you observe here on the right plot is not just micromotion? Like, as far as I understand, you're showing us stroboscopic dynamics, and then in between these stroboscopic cycles, there would be like oscillations. So if you would look at the system in a different stroboscopic cycle, so to speak, which would be determined by a different Floquet gauge, as you say, then you might see just the system freezing at a different amplitude level, so to speak.
Yeah, great question. So what's actually happening in between the kicks here, this is stroboscopic. We do look at a particular time, but the dynamics don't actually depend very sensitively on when we choose that time. Because if we're not kicking with the lattice, the Hamiltonian is just this left-hand term. The particles simply evolve kinetically in time. So you can see Talbot effects and things like that, but the dynamics are sort of maximally simple, and it's really in momentum space, and it's really the kicking with the lattice that allows you to kind of hop around and stir things up in momentum space. Did that answer the question?
Not quite, but maybe we can chat offline.
Okay. Maybe if it's still not clear at the end, ask again. I have maybe a few more bits of data that might be pertinent to it.
Yeah. Okay. Thanks.
Okay. So this is I would say varying the time reversal symmetry of the Hamiltonian, and you see that it turns on and off the quantum boomerang effect. And this slide is sort of going into more detail on the same phenomenon. So the point of this left-hand plot is it shows, as a function of that Fouquet gauge alpha, the expectation value of the momentum after 1 kick and after 25 kicks. So what you can see here is that the short time dynamics sort of depend on what you might consider the mean free path. But the long time dynamics depend on time reversal symmetry. And you can see that in this plot by the fact that the 25 kick curve is approximately odd under reflection around the point alpha equals 0.5. As a small detail here, maybe it's actually not exactly 0.5, it's a little bit less than 0.5 in our experiment, which is a consequence of the finite duration of the kicking pulses. Okay, and then another thing that you might try is, back to our original intuitive conception of the boomerang, you might try throwing the particle away from you in different directions or with different velocities. And in the case of this experiment, that corresponds to a different initial position offset of the primary lattice, the non-kicking lattice. And that's what's explored in this right-hand plot. So this phase phi is the spatial phase between the two lattices. And you see that for alpha near a half, the long time expectation value of momentum does not depend on that spatial phase, whereas if the Fouquet gauge is adjusted away from a half, it does depend on it. But they all the boomerangs with different initial positions all return to zero momentum if and only if time reversal symmetry characterizes the evolution. It's always nice as an experimentalist if you can make something to convince yourself that you can destroy it. And that can be done not only by adjusting the Fouquet gauge, but also by adjusting localization itself. So here we used a tool that I'm also going to mention in the second part of the talk, which has the effect of destroying the Anderson localization in the quantum kicked rotor. And this is, again, something pretty simple, a little bit related to the Fouquet gauge. So what we did here, as indicated in the cartoon at the top of the left-hand graph, is we added some random disorder, some random delay before each kick time. And so what we really did was we took some random parameter, but which is uniformly sampled from a distribution between minus delta over 2 and plus delta over 2, and added that to the time of each kick. And this actually controllably allows us to destroy the boomerang effect. So that's what's shown in this left-hand plot. You see the blue curve, which is a boomerang respecting non-disordered, zero disorder kicking waveform, which exhibits the quantum boomerang. And then if you just add in this disorder, for example, for delta equals 0.6, the average value of the momentum then becomes non-zero at long times. And that's sensible as shown in the second plot here, because actually localization has totally been destroyed in this model by this random kicking. So what's shown in the second plot is the energy as a function of kick number, and you see that far from localizing and staying constant as the quantum kicked rotor is supposed to do, it actually is growing. Almost looks like it's growing linearly with kick number. So that looks like it's a classical rotor undergoing Joule heating and absorbing energy from the drive. And so this disordered kicking sort of has the effect of turning the quantum kicked rotor into a classical rotor and then allowing it to delocalize. One might ask whether this is a phenomenon that has a particular onset at some critical disorder strength or turns on gradually from zero disorder, and it looks like the latter is the case. That's what the final graph in panel shows here, which plots the late time momentum after 25 kicks as a function of the disorder strength. And you see that it pretty much moves away from zero as soon as you turn on any disorder, and then gets further as the disorder strength gets stronger. Okay, so the main result of this first part of my talk about the quantum boomerang effect is that we observed and explored this recently predicted effect, which is a fundamental dynamical feature of Anderson insulating matter. And we looked at the dependence of this of the boomerang dynamics and the way that you can interfere with them by varying the Fouquet gauge and the temporal disorder to the kicking sequence. One thing that was not explored at all in this experiment that you might wonder about is the role of interactions. And how interactions affect the quantum boomerang effect is not something that we've actually looked at yet, at least not experimentally. But the next thing I want to talk about does involve interactions and the quantum kicked rotor. And that's this interaction-driven delocalization. So maybe before I move on to that, any other questions about the boomerang? Or a reprise of the question that I only partially answered before?
Yeah, maybe just a quick other question. So when you look at the energy, how it grows as a function of number of kicks, does it also happen when you change the flow gauge, or does it only happen when you change the disorder?
Good question. No, it only happens when you change the disorder. When you change the flow gauge, the system remains localized. It looks basically like the blue curve here, unless you add disorder. Okay. Great. Well, I'll go on to the second part and sort of try to go through it relatively quickly because I know I'm getting a bit short on time. So what we explored in this related experiment was a tunably interacting ensemble of quantum kicked rotors. And the physical realization here was using the same cold atom machine. So it was a lithium 7Bc and a periodically pulsed optical lattice. And the additional ingredient here was a Feshbach resonance. So non-cold atom specialists, a Feshbach resonance is a resonance between two free atoms and a molecule, which for our purposes basically gives us a knob to control the scattering length or the interaction strength between lithium-7 atoms simply by varying a DC magnetic field. So it lets you turn on and off the interaction strength and vary its amplitude. And this experiment really came from a lot of discussions and inspiration from Viktor Galitsky, our main theory collaborator for this project. And also we had a lot of good interaction with the group of Deep Gupta at the University of Washington, who were in parallel doing experiments exploring a similar phenomenon. And the resulting papers ended up being published back to back in Nature Physics. Okay, so what's shown here is a non-interacting quantum kicked rotor. And I didn't really show you this picture of it before, but this is what it looks like. So what you're seeing here is images taken in momentum space and stacked up left to right after every kick. So sorry the numbers are so small, but this is 0 kicks, 1 kicks, 2 kicks, and so on and so forth, all up to 25 kicks. And what you're seeing here are the occupation of the different momentum states in the lattice in momentum space. So what you see is the atoms start occupying some higher momentum states for the first few kicks, but then they stop. And the system is largely static for the last 15 or 20 kicks. So you're really seeing there visually the localization in the quantum kicked rotor. It doesn't keep going to higher and higher kinetic energy or higher momentum. It just stops evolving, even though we're hammering on this thing with an optical lattice with every single kick. So that's what it looks like in the absence of interactions. And if you take figures like that and sort of integrate them horizontally and stack them all up, you get a figure like this. So this is just showing the occupation of the various momentum states as a function of time. And now the only difference is I've made the x-axis logarithmic. And you can see that actually this very stable state with only a few momentum states occupied persists for like 1,000 kicks. So this is something that really lasts for a very long time. And what we asked ourselves, or what Victor asked us, is what happens if you turn on interactions in this prototypical localized system? You could imagine a few possibilities. You could hope for some sort of many-body dynamical localization. You could hope for delocalization. You could hope for pre-thermalization. And this is a topic which has been investigated with a lot of theoretical approaches, mostly mean field and numerical. But the validity of some of these approaches is a little bit hard to understand. And so we explored it experimentally. And what we saw was something like this. Really very different from the evolution of the system without interactions. And you see that there's some smearing out of the sharply occupied momentum space modes, and you can't really see here, but I'll show on future slides that you also see higher momentum modes getting occupied at late times when you turn on interactions. And the way that happens is pretty interesting. So what's shown here is the measured energy of this ensemble of kicked rotors as a function of kick number, again with the logarithmic x-axis. So this is going out to 1,000 kicks. And what you see is that after 10 kicks and up to maybe 100 kicks, all the rotors with different interaction strengths evolve about the same, and they come to rest close to this shaded prethermal plateau. But after that, sorry, I should have said the blue circles show non-interacting rotors, and the diamonds and squares show interacting rotors. And you see that after about 100 kicks, the interacting samples noticeably diverge from the non-interacting case. Something that's pretty interesting is the way that these interacting kicked rotors diverge from that prethermal plateau does not look classical still. If you do the trick we did before and randomize the kicking so that the system evolves classically, you get linear time energy growth. And that's plotted on the inset here. Those are experiments from the same, from the same day. That fast energy growth never occurs, even at very late times, for the interacting quantum kicked rotors. So we see this sort of subdiffusive delocalization, even at very strong interactions in very late times. So these quantum kicked rotors are absorbing energy much less well than their classical counterparts, even though they are absorbing it. And this destruction of localization, you can track it nicely by looking at the momentum space distribution. So these are linear and log axis plots of the momentum space distribution. And some of the features here, and in particular, the deviation from an exponentially localized distribution, are a little hard to track on these plots, although I think you can see them in panels D through F. But if you just graph the deviation from that exponential as a function of kick number, you see that it's actually a really sharp diagnostic of this interaction-driven delocalization. Okay, I think I should probably wrap up and try to take a few questions. But the main result of this second part of the talk is that we are able to tune interactions in an ensemble of quantum kicked rotors and see that those interactions drove delocalization, but non-classical delocalization away from what looks like a prethermal plateau. There's some things I didn't discuss here, which are pretty interesting and possible directions for future work. We did some studies of Low-Schmidt echoes, time reversal dynamics, and saw how that depended on interaction strength, which is actually non-monotonic, somewhat surprisingly. There's a mapping of the system to kicked spin chains, which is elucidated by in the supplementary info to our paper. And you can also play around with things that have been explored by other kicked rotor experimentalists, like fractional resonances, and look at the effective interactions on those. Maybe one other thing I should say is we saw an exponent of about a half, pretty close to a half, in this subdiffusive delocalization. And that actually matches pretty well some of the theoretical predictions for this. Not all of them, but some of them. And it's a little bit unclear to me why a mean field prediction would really work at all for this system where you have these really sharp collisions between atoms that are driving momentum redistribution. But the fact is that it does work, and there may be something interesting hiding in that fact. Okay, so to conclude, I told you really about two experiments. One of them was an observation of the quantum boomerang effect, which is a fundamental feature of Anderson localized matter. And then the second one that I just finished telling you about was a measurement of the interaction-driven delocalization of an ensemble of tunably interacting kicked rotors. So let me conclude by acknowledging everybody who did this work, certainly our theory collaborators, but also, of course, my graduate students, postdocs, and undergraduates who did all the hard work on these experiments. Roshan, who's in the red shirt in the middle here and who is defending his PhD on Monday, was the lead author of the quantum boomerang paper. And Alec, who I guess didn't come to the beach this day, that's terrible, or maybe had already graduated, was an amazing undergrad in my lab who was the lead on the quantum kicked rotor paper. And Alec is now in the group of Adam Kaufman at UC Boulder. So I thank all of them for their contributions. Of course, the funding agencies who supported the work. And I want to put in a little plug that, we do nice physics pretty close to the beach. You can walk to beaches like this from our lab. And I'm always looking for motivated and excited postdocs. So thank you finally to all of you for your attention. And I'd be happy to take questions if there are any.
Thank you, David. Questions?
So in the in the interacting experiment that you did, can you check that the system is really like remaining in the condensate as it's like departing from this localized regime?
I guess I wouldn't necessarily say that it is remaining in the condensate. I mean, we are, occupying a large number of momentum states. The condensate is occupying only the zero momentum state with some width around that depends on the physical size of the condensate. So this is, I mean, I think if we put this back in E, we would not find 100% condensed fraction the way we sort of almost start with.
Okay, I see. Is that then what you meant by like, it's unclear that the main field descriptions would apply? It's like if it's not...
No, I mean, what I meant by that, and maybe I'm just wrong, is that the dynamics of this experiment is, okay, we're adding a lot of momentum to the atoms with the optical lattice, and then two atoms scatter off each other in 3 dimensions, very sharply redistributing momentum between them. That's sort of not a very quantum mechanical picture. I'm thinking of them as little bowling balls, but it's a sharp effect. And it's not clear to me that a mean field picture should capture that accurately.
Any other question? So can I about the boomerang effect? So you explain it in terms of time reversal symmetry and localization. So now if one would think in terms of expanding in the eigenbasis, is there some simple picture how to see it out of that?
In momentum states, you mean?
Yeah. So you have a Floquet system, Floquet propagator, and then I would expand my initial state in the eigenbasis, where it seems much less intuitive.
Yeah, I mean, I'm not sure I have a good answer, but let me say one thing that may be at least a little relevant. There's an alternate loading procedure that you can do where instead of adiabatically loading the lattice, like it's shown in this little cartoon here, you kick on the lattice. It turns out that this is not at all obvious, but that populates the momentum states with different phases and actually destroys the quantum boomerang effect. It doesn't happen anymore at a Floquet gauge of 0.5. But if you go to a Floquet gauge of 0.75, you see that the boomerang effect happens again. And that can be understood from the time reversal symmetry point of view if you look at a sort of, sorry, I wish I had a slide on this, it's a little hard to describe, but if you look at a Talbot effect map of the evolution of the momentum states and time, you can actually just visually identify high symmetry points of that map where it has reflection symmetry. And those are exactly the points where the Floquet gauge, if you tune the Floquet gauge there, you get a quantum boomerang effect. So you don't have to have this particular sort of set of states, this particular set of phases and occupations of a momentum space eigenbasis for the boomerang effect to occur. But if you have a different one, you may need to tune the Floquet gauge to a different value.
Okay, I see. So any other question? Okay, if not, let's thank David again.
Thank you all for your attention.